Think about the robots we envision working alongside us. The humanoids, navigating busy warehouses, assisting in hospitals, maybe even, helping out at home.
Yeah, the demands are getting higher and higher.
Exactly. And the more complex the environment, the more we demand. But there's a sticking point, isn't there? How do we give them the brain power they need to operate effectively without making them these energy-guzzling, slow, ultimately not very practical things?
You've hit on a crucial point. It really feels like traditional computer processors are hitting their limits for these kinds of advanced tasks.
Right.
And that's where the idea of looking to biology for inspiration comes in. Specifically, brain-inspired chips or neuromorphic processors.
Neuromorphic.
For years, the human brain has stood out as the gold standard for incredibly efficient processing, just, unparalleled.
Right.
So researchers have been asking, could we design computing systems that fundamentally work more like it?
So not just faster versions of what we have now.
Exactly. It's not just about making things faster. It's about rethinking the very architecture of computation.
Okay, so this isn't just another incremental improvement in chip technology. This is like a completely different way of thinking about how we process information.
Precisely. Especially for something as demanding as robotics.
And that's exactly what we're diving into today. We're going to explore this fascinating field of neuromorphic computing.
Yeah, how mimicking the brain's design could really be a breakthrough for robotics.
And to make this less abstract, we're also going to focus on a really exciting real-world example.
Oh, yeah.
A new brain-mimicking device for robotics developed by researchers at RMIT University in Melbourne.
Ah, the RMIT work. Yes, that's a great example. We'll explore the fundamental principles that underpin this brain-inspired approach.
And the advantages it could bring, right? Like energy efficiency, speed.
Exactly. Vastly improved energy efficiency and incredibly fast reaction times. And by looking at the RMIT device, we can move beyond theoretical discussions.
See how it actually works in practice.
See how these principles are being applied in tangible ways.
Yes, right. It's not just a concept. There's actual hardware being built. So the goal of this deep dive is clear. We want to understand the core mechanics of neuromorphic computing, why it holds so much promise for the future robotics.
And really dig into that RMIT vision system.
Yeah, how it functions at a material level, what it's capable of, and what it tells us about where this field is headed.
Okay, so let's start by understanding what makes neuromorphic computing such a departure from the norm.
Where does it diverge from, say, my laptop processor?
It all comes down to its fundamental architecture compared to the computers we use every day. In traditional computers, there's a clear separation.
Right, CPU and memory.
Exactly. The central processing unit, where all the calculations happen, and the memory, where the data is stored.
And that works. Mostly?
It has worked well for many applications, sure, but it creates a bottleneck.
The infamous von Neumann bottleneck.
That's the one.
All that constant shuttling of data between the processor and the memory, it just slows things down.
And consumes a lot of power, especially when a robot is dealing with a constant flood of information from its sensors. Think cameras, LiDAR.
Yeah, a continuous stream.
Exactly. Neuromorphic computing essentially throws that blueprint out the window.
Okay, starting fresh.
Instead, it integrates memory and processing directly, right there at the level of the artificial neurons and synapses.
Like in our brains.
Precisely. Think about the neurons in your brain. They don't have separate memory banks. The connections themselves, the synapses.
That's where the action happens.
That's where information is both stored and processed. And this fundamental shift in architecture has some profound implications.
Okay, like what specifically? What are the core design principles that allow these neuromorphic chips to function in a brain-like way?
Okay, one key principle is event-driven computation.
Event-driven?
Yeah, it uses spiking neural networks, or SNNs, unlike traditional systems that are constantly processing information, sort of grinding away.
Like crunching numbers constantly.
Well, SNNs operate more like our own neurons. They fire off discrete spikes, little electrical pulses, but only when they receive a sufficient amount of input.
So only when something actually happens.
Exactly. This is incredibly energy efficient because the system is only active when something significant is happening.
Okay.
And because these spikes occur in time, SNNs are inherently well suited for processing temporal data.
Like video streams or sound.
Exactly. The continuous streams of sensory information are robot encounters. Imagine it like a security system that only records when it detects motion, rather than recording 24/7.
That makes perfect sense for saving energy. So instead of continuous stream of data being crunched, It's more like a series of quick messages being passed around only when they're needed.
You got it.
What other brain-inspired tricks are at play here?
Another crucial principle is parallel processing.
Okay.
Our brains contain billions of neurons and trillions of connections all working simultaneously. Just mind-boggling parallelism.
Yeah, hard to even comprehend.
Neuromorphic chips aim to replicate this massive parallelism with vast numbers of artificial neurons and synapses operating concurrently at the same time.
So they can handle lots of inputs at once.
Exactly. Handle complex data from multiple sensors in real time, something that can easily overwhelm traditional processors that handle tasks more, sequentially, one after another.
Right.
Think of it as having a huge team of specialists all working on different aspects of a problem at the same time, instead of one person trying to do everything.
Okay, so a multitude of tiny processing units working together simultaneously. Makes sense. And you mentioned in-memory processing earlier. How does integrating memory and computation directly overcome that von Neumann bottleneck we talked about?
It essentially bypasses it altogether.
Just sidesteps the whole problem.
Pretty much. Instead of constantly moving data back and forth between separate memory and processing units, the computation happens right where the data resides.
Within the artificial synapses and neurons themselves.
Exactly. This drastically shortens the distance the data needs to travel.
Which means faster processing.
Much faster processing speeds and significantly lower energy consumption.
Right.
It's like having all the reference materials you need embedded directly in your fingertips while you're working on a project.
Instead of running to the library constantly.
Exactly. Rather than having to get up and go to a library every time you need to look something up.
That's a great analogy. Less travel equals less wasted energy and faster results. Okay. Now, our brains are also incredibly good at learning and adapting. That seems key for robots.
Absolutely crucial.
How do neuromorphic chips handle that?
That's where synaptic plasticity and adaptive learning come in.
Plasticity, like flexible connections.
Exactly. Neuromorphic systems aim to mimic how the connections between our neurons, the synapses, can change in strength based on their activity.
Learning from experience.
It's inspired by fundamental principles of neuroscience, like Hebbian, learning the idea that neurons that fire together wire together.
Heard that one before.
And long-term potentiation. By dynamically adjusting the weight or strength of these artificial synaptic connections, the system can learn and adapt to new information.
Without needing to be completely reprogrammed.
That's the key. It's a form of continuous on-chip learning.
So these chips can essentially learn and adjust on their own, adapting to new situations without us having to go back and rewrite their code. That sounds like a massive advantage for robots that will inevitably encounter unexpected situations in the real world.
Precisely. A huge advantage. And these core principles translate into some really compelling advantages for AI and robotics.
Let's talk specifics.
We've already touched on energy efficiency, which is absolutely critical for autonomous robots that rely on battery power.
Right. Untethered robots need to last.
We're talking about the potential for a dramatic reduction in energy consumption for certain tasks. For instance, research has demonstrated drones using neuromorphic processors that can process data significantly faster while using far less energy. And there's the NeuRAM chip, which has shown remarkable energy efficiency for specific types of AI algorithms.
Orders of magnitude better, potentially.
Potentially, yes, for the right tasks. If robots could operate for days instead of hours on a single charge, think about the new roles they could realistically take on.
Things that are just infeasible now.
Right. Continuous environmental monitoring or extended search and rescue operations.
That kind of efficiency could truly unlock a new era of mobile robotics. Okay, what about their speed? How quickly can they react to things happening around them?
That's where real-time processing and low latency are key.
Low latency meaning minimal delay.
Exactly. Because of their event-driven nature and massive parallelism, neuromorphic chips can process information almost instantaneously.
Really fast.
This is absolutely vital for robots that need to interact with dynamic environments, react to sudden changes, or perform tasks requiring very precise timing.
Like dodging obstacles or catching something.
Consider a humanoid robot working in a busy factory. It needs to be able to see a moving cart and adjust its path in a fraction of a second to avoid a collision.
No time for slow processing there.
Definitely not. SNNs are particularly well suited for handling these kinds of continuous, rapidly changing data streams that robots deal with.
So they could perceive, process, and react in what feels like the blink of an eye.
Okay. And you mentioned adaptability again. This ability for on-chip learning to adjust. to new circumstances without needing extensive retraining, that's a huge benefit for robots that will be deployed in unpredictable environments.
Exactly. Imagine a robot working in agriculture.
Okay.
It suddenly moved to a different field with a new type of crop. A neuromorphic system could potentially learn to identify the new plants and adapt its harvesting techniques.
All by itself.
Without requiring a complete reprogramming, yes. This kind of long-term adaptability could significantly reduce maintenance and improve the overall lifespan and utility of robotic systems. This all sounds incredibly promising. Are there any major players in this field, like companies actually building these things?
Yes, definitely. There are some very innovative companies and research groups making significant strides. Intel, for example.
Oh, Intel's involved.
Yeah, they have their Loihi processor. It utilizes asynchronous spike-based processing and features a vast number of programmable neurons.
Wow.
It even incorporates sophisticated mechanisms for the artificial synapses to learn and adapt using optimized learning rules.
So they're tackling that learning aspect directly.
They are. Then you have BrainChip with their Akida platform.
Akida.
Akida. It's designed for ultra-low power AI inference right at the edge.
At the edge, meaning on the device itself.
Exactly. Ideal for applications like smart surveillance cameras or autonomous vehicles where rapid local decision-making is essential without relying on cloud connectivity.
Ultra-low-power AI inference at the edge. That sounds like exactly the kind of technology that could make truly mobile and autonomous robots a reality.
It is. This move towards decentralized intelligence is really significant. For many applications, especially those where internet connectivity is unreliable.
Or where lag is dangerous.
Right, or where even small delays can have critical consequences, having the processing power located directly on the device is a huge advantage.
Yeah, absolutely.
And it raises a fundamental question, really. As we shift from purely symbolic computation to systems that learn and adapt more organically, are we witnessing a reevaluation of what computation itself means?
Huh. What do you mean?
Could we see phenomena like self-organization and emergent behavior becoming integral parts of our definition of computing, moving beyond just calculation?
That's a profound thought.
Yeah.
It's like we're moving beyond simply calculating to something that more closely resembles understanding, or at least reacting intelligently.
Perhaps. It's an intriguing direction.
Now, to really clarify the core differences between these approaches, you mentioned a table earlier, or just summarizing the key distinctions.
Right. Let's lay it out. Fundamentally, the architecture, integrated memory and processing in neuromorphic versus separate units in conventional von Neumann systems.
Got it. Processor and memory together versus apart.
Then the processing mode. Neuromorphic uses event-driven asynchronous processing with spikes. Traditional systems are typically clock-driven, processing step-by-step, sequentially.
Mics versus clocks.
This difference enables massive inherent parallelism in neuromorphic systems. Achieving that in conventional systems often requires significant extra engineering effort.
Parallelism is built in versus bolted on.
You could say that. Energy efficiency for AI tasks. Neuromorphic often shows orders of magnitude improvement.
Huge energy savings.
For the right tasks, yes, learning. It's adaptive and occurs directly on the chip in neuromorphic systems. Conventional AI models typically need offline training.
Learning on the job versus learning in the classroom.
Good analogy. Strengths. Neuromorphic excels in real-time, low-power processing for dynamic, sensory-rich data. Think robot senses. Conventional systems are great general-purpose computers and shine in tasks needing high precision.
Different tools for different jobs.
Exactly. Limitations exist too, of course. Neuromorphic systems are still facing challenges in scaling up and the maturity of the development tools, the software side.
Still early days in some ways.
While conventional systems are increasingly constrained by that von Neumann bottleneck and high power consumption for complex AI,
So ultimately,
neuromorphic computing is proving to be particularly well suited for dynamic AI applications where speed, efficiency, and adaptability are paramount, like advanced robotics.
okay, that really clarifies the fundamental differences and the exciting potential. Now, let's delve into that specific innovation you mentioned earlier, the neuromorphic vision system coming out of RMIT University.
Yes, the RMIT work.
What exactly have they managed to create? It sounded pretty impressive.
It is a truly groundbreaking piece of work. Researchers at RMIT have developed a proof-of-concept device.
Proof of concept, so still experimental.
Yes, but capable of detecting hand movements, storing memories of those movements, and processing this visual information, all without relying on an external computer.
Wow. All in one package.
a self-contained, brain-inspired vision system. This significant research was recently published in Advanced Materials Technologies, which really underscores its importance in the field.
That's remarkable. A single device that can essentially see, remember, and process visual information independently. Who is the team behind this innovation?
The core research team is RMIT's Center for Optoelectronic Materials and Sensors, or COMAS. It's led by Professor Sumit Walia.
Okay.
He's the director of COMAS and a key author. The first author who played a central role is Tiha Ong, an RMIT PhD scholar. Also key are Professor Akram Al-Hourani, the deputy director of COMAS, and Dr. Tamer Ahmed. They were all critical contributors.
So a dedicated team pushing the boundaries of what's possible. How does this device actually function? How does it mimic both the eye and the brain?
Okay, the key lies in the material they're using. Molybdenum disulfide, or monas-2-2-tol.
Monocells. We'll probably talk more about that later.
Definitely. They've engineered this material at an atomic level to create specific defects, little imperfections.
On purpose?
Yes, intentionally. These atomic scale defects are designed to capture incoming light and directly convert it into electrical signals.
So the material is the sensor.
In essence, yes.
Yeah.
This is how the device mimics the function of the photoreceptor cells in our eyes.
That's incredibly clever. And you mentioned it can detect movement without having to process entire video frames.
Yeah.
How does it achieve that efficiency?
This is where the principle of movement detection through edge detection comes into play.
Edge detection, focusing on outlines.
Sort of, instead of capturing and analyzing every single pixel and every single frame of a video stream, which is very data intensive.
And power hungry.
And power hungry, yes. The device focuses on identifying changes or contours within the visual scene. Think of how your own eye and brain quickly notice the outline of a moving object against a static background.
You don't consciously process the whole wall, just the person walking past it.
Exactly. By focusing on these changes in edges and boundaries, the RMIT device needs to process significantly less data compared to traditional frame-by-frame analysis.
Which means lower power requirements.
Much lower power requirements. This work builds upon their previous research with still images, mind you.
Okay.
But it represents a crucial step towards more dynamic and efficient visual processing, which is essential for robots that need to react to movement in their environment.
Right, like that robot navigating a crowded room. It only needs to focus on the moving people, not the static furniture.
Precisely.
So it's not trying to see and process everything all the time, just the important changes. That sounds vastly more energy efficient. And how does it store these detected movements as memories directly within the device? That sounds sci-fi.
It's another ingenious aspect of their design. The device is engineered so that these detected visual events, these changes and movements, are stored directly within its physical structure.
No separate memory chip needed.
Correct. It completely eliminates the need for separate external memory units and perfectly embodies that neuromorphic principle of in-memory processing we discussed.
Wow.
And importantly, these memories aren't permanent. They can be reset. This allows the device to continuously process new visual information.
So it can learn, forget, and learn again.
In a sense, yes. This ability to process and remember information locally, right at the sensor level, without needing to transmit large amounts of data to a separate computer, that's what we mean by processing at the edge.
Edge computing again.
It significantly reduces data transmission, power consumption, and latency. Big wins.
Okay, so it can see movement, process that information in an energy-efficient way, and store it locally. That's already impressive for a single device. But you also mentioned it mimics neural behavior.
Yeah.
How does it do that at a fundamental level?
Right. The RMIT device is specifically designed to emulate the behavior of a neuron according to the Leaky Integrate and Fire, or LF, model.
LF model.
It's a foundational model in computational neuroscience. It captures the essential dynamics of how many biological neurons operate, albeit in a simplified way.
Leaky, integrate, and fire. That sounds quite technical. Can you break that down for us?
Certainly. Let's try an analogy. Think of a neuron as a tiny electrical bucket, or maybe a capacitor in an RC circuit.
Okay, a leaky bucket.
Incoming signals from other neurons are like adding water or charge to the bucket. That's the integrate part.
Filling it up.
But the bucket isn't perfect. It has a small hole, so it gradually loses some water over time. That's the leaky part. Represents passive ion channels in a real neuron.
Okay, so it loses charge slowly.
Right. Now, if enough water gets poured in quickly enough to reach a certain level, a threshold,
The bucket overflows.
the neuron fires. It generates an electrical spike, like tipping the bucket over. After firing, the bucket is quickly emptied, the reset, And there's a brief period where it can't be filled or fire again, the refractory period.
Got it. Integrate, leak, hit threshold, fire, reset.
That's the essence of it. The LF model, while a simplification of real neuronal behavior, captures this crucial process of integrating incoming signals over time, firing when a threshold is reached, and then resetting.
Okay, I think I'm getting the picture. It's about accumulating input, firing when it reaches a certain level, and then resetting itself. But how does this MS-22 material actually achieve that kind of behavior?
Yeah.
It's just a material, right?
That's where the connection between material science and neurobiology becomes really fascinating. It's not just luck.
Not a coincidence.
No. The ability of this MS-22 device to mimic the LF model is deeply rooted in the material's electronic properties at the atomic level.
Okay.
The specific way that MS-22 behaves electrically and how that behavior is influenced by those engineered defects like the sulfur vacancies we mentioned.
The intentional imperfections.
Right. Those likely provide the nonlinear dynamics needed for this integrate and fire functionality.
Nonlinear dynamics.
Yeah.
Meaning it doesn't just respond proportionally.
Exactly. Consider this. The material needs to be able to accumulate an electrical charge in response to light, exhibit a gradual leakage of that charge over time, reach a point where it suddenly releases that charge, the firing, and then quickly return to its initial state.
So it needs to do all those Aleph steps physically.
Precisely. And the fact that we can tune the properties of MS-22 at the nanoscale by controlling the types and density of these defects seems to provide the physical mechanisms for these distinct integration, firing, and reset phases.
So the material itself is engineered to act like a simple neuron.
Effectively, yes, making the material itself behave like a simplified neuron.
So it's not just about the way the device is architected. The very material it's made of is engineered to behave like a neuron at a fundamental level. That's a truly profound connection between material science and computing.
Absolutely. It highlights how advancements in nanotechnology are directly enabling these new paradigms of brain-inspired computation.
Now, you mentioned this is a proof of concept. What are the current limitations? What hurdles need to be overcome for this RMIT system to become a practical technology?
Yeah, important to be realistic. The primary limitation at this stage is that it's a single pixel device.
Just one point of light detection.
Essentially, yes. While it can detect movement in a very localized way, it's not yet a full-fledged vision system capable of processing high-resolution images like a camera.
So, not seeing the whole picture yet.
Not yet. The researchers themselves clearly state that it's a simplified model of the brain's incredibly complex visual processing capabilities.
Okay, so it's a significant first step, a building block, but there's still a considerable amount of work needed to scale it up to something that could provide, say, useful visual information for a robot.
Exactly. Scaling is a major challenge.
To summarize this exciting RMIT innovation, then, can you give us the key takeaways? What should we remember?
Certainly. Key points. It's a neuromorphic vision system. The core technology uses molybdenum disulfide, MUSTER-S22, with specifically engineered atomic scale defects.
Okay, MUSTER-S22 with defects.
It mimics the eye by using these defects to capture light and convert it to electrical signals.
Distinct light.
And it mimics the brain by processing information and storing memories locally within the device itself in memory processing.
Processing and memory together.
It demonstrated dynamic movement detection through edge detection, focusing on changes. And it emulates the leaky integrate and fire, LIFF, neuron model.
Movement detection and LIF behavior.
A key feature is its potential energy efficiency thanks to analog processing and only processing changes.
Saving power.
Currently, it's a single pixel proof of concept. Key researchers: Professor Walia, Tiha Ong, Professor Al-Hurani, Dr. Ahmed at RMIT, and the work is published in Advanced Materials Technologies.
That gives us a really clear understanding of this exciting development. Thanks. Now let's broaden our view again and talk more about this fascinating material, molybdenum disulfide, or molybdenum-2 You've mentioned it a few times. Why is it attracting so much attention in the field of neuromorphic design?
Right, MUS-2. It's rapidly becoming recognized as a crucial enabling material for the next generation of neuromorphic devices.
Enabling material, meaning it makes these new designs possible.
In many ways, yes. It belongs to a family of materials called transition metal dichalcogenides, or TMDCs.
TMDCs, okay.
And it possesses a unique combination of properties that make it exceptionally promising for mimicking biological neural functions at the nanoscale.
What makes it so special compared to, say, good old silicon?
Well, for one thing, as we touched on, it's essentially atomically thin. It's a two-dimensional material.
2D material, like graphene.
Similar concept, yes. This ultra-thin structure, sometimes just a single layer of atoms thick, allows for very precise electrostatic control over its electrical properties.
More control than with thicker materials.
Exactly. You get a very high surface-to-volume ratio, and some unique quantum mechanical effects come into play. This means we can really fine-tune its electrical characteristics in ways that aren't possible with bulkier 3D materials like silicon.
Okay, fine-tuning is key.
Plus, it's mechanically flexible.
Flexible, so you could bend chips made from it?
Potentially, yes. And it has the potential for cost-effective manufacturing at large scales. These attributes make it ideal for creating the ultra-compact and highly energy-efficient components needed for advanced neuromorphic systems.
So it's incredibly thin, its properties can be precisely controlled, it's flexible, and it can potentially be manufactured at scale. That sounds like a materials scientist's dream for building tiny electronics.
It certainly generated a lot of excitement.
What specific properties of MAMR-STO2 are being leveraged in these neuromorphic devices? You mentioned the defects.
Right, the atomic scale defects like sulfur vacancies. Again, these aren't just random flaws, they can be intentionally engineered.
Designed in.
Yes. And used not only to capture light, as we saw in the RMIT device, but also to precisely control the neuromorphic characteristics of the material itself. By carefully managing these defects, we can influence how electrical charges are trapped and move within the material.
Which is fundamental for making artificial synapses.
Exactly, for creating artificial synapses and memory elements. It's a very sophisticated approach, actively structuring materials at the atomic level to impart specific dynamic behaviors that mimic neural components.
So these defects are almost like designed functional units within the material itself.
Very cool.
What other capabilities does MAMR-STO2 offer that are beneficial for neuromorphic computing?
Another key property is resistive switching.
Resistive switching, like changing resistance.
Exactly. MAMR-STO2 can be used to fabricate devices known as ReRAM, or resistive random access memory. They function similarly to memristors.
Memristors, the memory resistors.
That's them. These devices can change their electrical resistance depending on the history of the voltage applied to them. Very much like how the strength of the connections between neurons, the synapses, changes with activity.
So that's the basis for synaptic plasticity.
Precisely. It allows the device to remember past activity. MAMR-STO2-based memristors have demonstrated excellent performance characteristics, including very low power consumption and switching voltages that are even comparable to the electrical signals in biological neurons. Think around 400 millivolts.
400 millivolts. That's tiny. Definitely crucial for achieving the kind of energy efficiency we're aiming for. What about the speed at which these devices can operate?
Good question. The ultra-thin nature of MAMR-STO2 also facilitates efficient charge transport and fast switching speeds.
So electrons move easily and quickly.
Relatively speaking, yes, which is absolutely essential for building high-performance neuromorphic circuits that can process information rapidly.
And I recall you mentioning that MAMR-STO2 is also sensitive to light. You said optoelectronic properties.
Yes, exactly. OSS2 exhibits interesting optoelectronic properties. It's photosensitive, as the RMIT device shows.
Right.
And researchers have gone further, developing arrays of MOS22 transistors that, when combined with elements like golden nanoparticles, can actually simulate synaptic behaviors using light.
Using light to mimic synapses. How?
It allows for optical writing, erasing, and even direct processing of image data on the chip itself. There have been demonstrations of using these kinds of arrays to store simple images, like emblems, and even to achieve a high degree of accuracy, like 96.5% in recognizing handwritten digits processed optically.
So we could potentially have chips that learn and process visual information directly using light signals, not just electrical ones.
Yeah.
That's a really fascinating prospect. What are the overarching advantages, then, of utilizing MOS22 in neuromorphic systems? Summing it up.
Okay, the main advantages boil down to 1, low power consumption due to those low switching voltages and efficient charge transport in thin films.
Power saving. Got it.
2, scalability and miniaturization. Its 2D structure allows for the creation of incredibly compact and high-density arrays of devices. Think fitting more processing power into smaller spaces. We've seen small integrated arrays, maybe 0.7 by 0.7 centimeters square, combining sensing, memory, and processing.
Tiny but powerful.
3, the potential for direct interfacing with biological neural tissues in the future.
Connecting chips directly to nerves or brains.
That's a long-term vision, but because its operating voltage range, like that 400 millivolt figure, is similar to the signals in our own brains, it opens up possibilities.
Wow. Okay, that combination of small size, low power, high functionality, and potential biointerfacing is precisely what's needed for embedding intelligence into robots and other compact devices.
Exactly.
It sounds like this focus on materials like MOS-S22 is a key part of the strategy to overcome the limitations of traditional silicon-based computing, the more idea you mentioned.
Absolutely. It aligns perfectly with the more than more trend in the semiconductor industry. Innovation isn't just about shrinking silicon transistors anymore.
It's about new stuff.
It's about exploring new materials, new device architectures, leveraging entirely different physical phenomena at the nanoscale to achieve breakthroughs in computational capabilities, especially in terms of energy efficiency.
So MANIS2GO isn't just another alternative material. It's a potentially transformative component in the development of brain-inspired computing. To really summarize its significance, could you give us a quick rundown of its key properties and how they relate to its applications in neuromorphic systems, like a cheat sheet?
Okay, quick cheat sheet for MANIS2D2 in neuromorphic systems.
Lay it on me.
Atomic structure. Ultra-thin, 2D, allows compact, sensitive devices.
This is good.
Electronic properties, tunable, versatile for different functions. Role of defects. Engineered defects control characteristics, enable memristive behavior for synapses.
Defects are features. Got it.
Resistive switching. Allows for memristors, fundamental for in-memory computing.
Memory inside.
Optoelectronic behavior. Sensitive to light, enables light-based sensing and processing.
Sees light.
Scalability. Suitable for high-density arrays, complex systems.
Big lock of them.
Contribution to low power. Low operating voltages mean energy efficiency. Potential for biointerfaces.
Saves power. Might talk to brains.
That's the essence of why it's so exciting for this field.
Okay, that's a fantastic overview of why MANIS2 is generating so much excitement. Now, let's tie everything together. We've talked about neuromorphic principles, the RMIT device, this amazing material. How could the integration of all this neuromorphic computing with advanced materials like MANIS2 really revolutionize the capabilities of humanoid robots?
This integration, it really has the potential to unlock truly transformative capabilities, especially for humanoid robots operating in complex, unpredictable, human-centric environments.
Okay, let's break that down. Start with how they perceive their surroundings. You mentioned enhanced perception and situational awareness earlier. What would that look like in practical terms for a robot?
Imagine instant visual processing instead of laboriously analyzing whole video frames.
Like current robots often do.
Right. Neuromorphic vision systems could detect changes and important features in their environment almost instantaneously. This rapid processing is absolutely critical for enabling quick reactions in dynamic situations.
Seeing and reacting much faster.
Exactly. And then there's edge detection, similar to what the RMIT device demonstrated. This allows robots to efficiently identify objects and changes using significantly less data and power.
Focusing on what matters.
It mirrors how our own visual system prioritizes key visual information movement outlines. It's a much faster and more energy-efficient way for robots to understand what's happening around them.
So if we think back to those clunky, power-hungry robots we started with, this energy efficiency you're describing could be a game changer for making them truly practical, right?
Yeah.
Being able to react faster and more efficiently would make them much safer and more effective, too.
Absolutely. Safety and efficiency go hand in hand here.
What about how long they can operate independently? Battery life is always a killer for mobile robots.
That's where unprecedented energy efficiency really comes into play. Analog processing, which is a core feature of many neuromorphic systems.
As opposed to digital.
Right. It can drastically reduce the energy consumption required for complex visual tasks compared to traditional digital technologies. They're only processing the information that is actually relevant at any given moment, not wasting energy on static background details.
That sounds huge.
This level of energy efficiency is a potential game changer for achieving long-term autonomy, allowing robots to operate for significantly extended periods on a single charge.
Days instead of hours.
That's the hope for certain applications. It could fundamentally alter the kinds of tasks they can realistically undertake.
So if robots could operate for days instead of hours, what new roles might they realistically take on that are currently infeasible? Continuous monitoring in remote locations. Providing constant assistance to someone in need.
Exactly those kinds of things. Tasks requiring persistence and presence over long durations.
Longer battery lives would definitely overcome a major limitation of current mobile robots. Okay, what about their ability to make decisions and interact with humans in a natural way?
Real-time responsiveness and decision-making will be significantly enhanced.
Faster thinking.
You could put it that way. The low latency of neuromorphic processing will enable robots to react more quickly and make more timely decisions, crucial for safe navigation and seamless interaction with humans.
Less lag between seeing and doing.
Precisely. And because spiking neural networks are particularly adept at handling dynamic and temporal data, they'll be better equipped to understand and respond to complex, evolving situations.
So they can handle the messiness of the real world better.
That's the idea. And when it comes to improved and more natural human-robot interaction, or HRI...
making them less robotic.
Exactly. The potential is enormous. The ability to recognize and react to subtle human cues, gestures, facial expressions, maybe even changes in tone of voice with minimal delay can lead to much more fluid and intuitive interaction.
Like talking to a person almost.
Moving in that direction, as Professor Alarani from RMIT pointed out, this could significantly enhance their effectiveness and user acceptance in roles like manufacturing and personal assistance.
People might actually like working with them.
More natural and responsive HRI could even help bridge the uncanny valley, that creepy feeling some robots give off.
Yeah, definitely know that feeling.
And foster greater social integration of robots.
So we're talking about robots that can not only see and react faster, but also understand and interact with us in a more intuitive and human-like way. It's moving beyond just basic automation to true collaboration.
That's the vision, yes.
You also mentioned that the applications extend beyond just humanoid robots. What other fields could benefit from this technology?
Oh, the potential is incredibly broad. Think about autonomous vehicles.
Cars, trucks.
With significantly improved response times in critical situations, huge safety implications.
Definitely.
Edge AI and IoT devices, Internet of Things. Imagine smart sensors that are always on but use almost no power.
Until something happens.
Right. Performing real-time monitoring and analysis locally. Advancements in healthcare wearable devices that can process complex biomedical signals efficiently.
Like smarter health trackers?
Potentially much smarter, yes. And even cybersecurity systems that can adapt and detect novel threats in real time, perhaps identifying unusual patterns faster than traditional methods.
It sounds like the integration of neuromorphic computing and these advanced materials could have a truly transformative impact across a wide range of industries. But, okay, we also need to be realistic about the challenges involved in bringing this technology to fruition. You mentioned scaling earlier. What are the major hurdles that still need to be overcome?
You're absolutely right. The journey from laboratory breakthroughs like the RMIT device to widespread real-world applications is always filled with challenges. Big ones.
Such as?
One significant hurdle is scaling and complexity. Moving from single-pixel proof-of-concept devices to high-resolution vision systems with anything approaching the intricate processing capabilities of a biological brain, that's a massive technological leap.
Going from one neuron to billions.
Essentially, yes. Current neuromorphic systems are still highly simplified models. Then there's the issue of material consistency and fabrication.
Making them Ovedi to Sility too.
Exactly. Ensuring that novel materials like Momosuidi can be produced with uniform properties and reliable performance across large-scale manufacturing processes, that's a significant engineering challenge. You need every chip, every pixel to work consistently.
Right.
The fact that achieving uniform wafer-scale, highly stable device structures is a recognized area of active research really underscores this challenge.
Consistency and reliability at scale are always difficult when dealing with new materials. What about the software side of things? Are the algorithms and training methods ready for these new types of processors?
That's another critical area. Algorithm development and training for spiking neural networks. We don't always have effective methods for translating traditional deep learning algorithms, the ones used everywhere now.
Like for ChatGPT or image recognition?
Right. Translating those effectively to these spike-based networks isn't straightforward. Developing new learning algorithms that can fully leverage the unique capabilities of SNNs and training them efficiently is an active and ongoing area of research.
We need new ways to program them.
We do. Intel's development of optimized learning rules for their Low-E2 chip is a direct response to this challenge. They know it's crucial.
Okay.
And perhaps less obvious but equally important is the need for a mature and comprehensive software ecosystem.
The tools for developers.
Exactly. User-friendly programming models, specialized algorithms optimized for neuromorphic hardware, effective debugging tools, standardized interfaces. all the things that allow a broader community of researchers and developers to actually use these novel platforms effectively.
So it's not just about building the hardware. We also need the right tools and techniques to program and utilize these brain-inspired chips effectively.
Yeah.
What about how these new systems will interact with the existing computing infrastructure? Will my neuromorphic robot talk to my regular computer?
Good question. Integration with conventional computing systems will be crucial. Neuromorphic systems are not likely to completely replace traditional CPUs and GPUs in the near future, if ever.
They'll work alongside them.
Most likely, yes. They'll function as specialized co-processors, accelerators for specific tasks they excel at, like sensory processing or pattern recognition. Therefore, we need to develop seamless and efficient ways for them to integrate and exchange data with existing computer architectures. They need to play nicely together.
So it's a multifaceted challenge that requires progress in materials science, chip design, algorithm development, software tools, and system integration.
Wow. What kind of research is currently underway to address these hurdles? Where's the focus?
There's a tremendous amount of exciting research happening across all these fronts. A major focus is clearly on scaling up the current technologies.
Making them bigger and more complex. Right. Creating larger pixel arrays for vision, integrating more neurons and synapses, and putting them into complete functional systems.
Yeah?
You mentioned the ARC's Life Grant awarded to RMIT that's specifically aimed at facilitating this kind of scale-up research infrastructure.
Okay, scaling is job one. What else?
We're also seeing significant exploration of new materials. Beyond MOS 282, researchers are looking at other 2D materials or other novel materials entirely that might offer even better or complementary properties for neuromorphic devices.
Maybe materials better suited for different senses.
Perhaps, or extending sensing capabilities beyond the visible light spectrum into infrared for heat sensing, or UV, maybe even for chemical sensing for applications like emissions tracking or contaminant detection.
Interesting.
There's also a strong drive towards optimizing neuromorphic devices for specific real-world applications, tailoring the hardware and software for particular tasks, constantly pushing for lower power consumption and enhanced performance for those tasks.
Making them really good at one thing, maybe.
Initially, perhaps. The understanding is also growing that these systems will likely be complementary to traditional computing, as we discussed. This leads to more collaborative efforts in hardware-software co-design, designing the hardware and software together from the start.
Smarter design process.
Definitely. Furthermore, research is ongoing into developing more sophisticated neural models that go beyond the basic LIF neuron, incorporating more biological realism where it provides a clear benefit, but without adding excessive complexity that makes them too hard or slow to simulate.
Finding the right balance of realism and efficiency.
Exactly. The development of hybrid architectures that combine the strengths of analog neuromorphic processing for efficiency with the precision of digital electronics for control or specific calculations is another important trajectory.
Best of both worlds.
That's the goal. And fundamentally, the field requires a new generation of interdisciplinary engineers and researchers. People who understand material science, like MODS S2 engineering, neuroscience, to understand biological models like LIF, electrical engineering, for the actual device design and system integration. It really sits at the intersection of many fields.
It sounds like a really vibrant and collaborative field with a lot of exciting avenues of research being explored. Okay, the big question. What's your best estimate for when we might start seeing these advanced neuromorphic vision systems appearing in everyday technologies? Are we talking next year, 5 years, 20 years?
Yeah, the timeline question. It's important to maintain a realistic perspective here. Leading researchers in the field, including those at RMIT, generally agree that widespread adoption of advanced neuromorphic vision in everyday technologies is likely still many years away.
Okay, so not next Christmas.
Probably not, no. However, the pace of progress is undeniably rapid and very encouraging. The fact that we're seeing the development of provisional patents for novel innovations?
Like the RMIT team filed.
Exactly, and significant research funding being allocated to this area. These are strong indicators of a very active field that is achieving meaningful milestones in the near term. We'll see incremental progress and perhaps niche applications sooner rather than later.
Well, this has been an incredibly insightful deep dive into the fascinating world of neuromorphic computing and the exciting innovations happening, particularly with the RMIT vision system, and the remarkable potential of materials like MODS S222.
It's definitely an exciting space to watch.
It's clear that this brain-inspired approach holds the key to overcoming some fundamental limitations in current AI and robotics, especially when it comes to energy efficiency and real-time processing.
Absolutely. Those are the big drivers.
This could truly pave the way for the development of truly adaptive and, dare I say, cognitive robots capable of operating with sophisticated autonomy in complex human environments.
With profound implications across numerous fields, as we discussed.
It's truly remarkable how much we can learn by looking at the elegant efficiency of biological systems, right? And how that's driving cutting-edge innovation in engineering. Biomimicry at its finest.
Nature's had billions of years to optimize after all.
Good point. While there are certainly significant challenges that still need to be addressed, scaling, materials, software...
Challenges, yes.
The continuous advancements we're witnessing in material science, device engineering, and the development of specialized algorithms, as beautifully exemplified by the RMIT system and other MUSIS-2-based devices, strongly suggest a future populated by much more intelligent and energy-efficient machines.
The trajectory is definitely positive.
And it's maybe worth stressing, the goal isn't necessarily to perfectly replicate human intelligence, right? But to create significantly more capable and versatile machines using these principles.
That's a crucial distinction, yes. Inspiration, not necessarily duplication.
Right. And as we continue to move towards creating machines with more nuanced perception and the capacity for more natural interactions, it really prompts us to consider the increasingly blurred lines between biological and artificial intelligence.
It certainly raises some deep questions.
Yeah, and the important societal implications that we need to be thinking about proactively as these technologies mature.
Yeah.
Even if widespread deployment is still, as you say, many years away, maybe starting that conversation now is pretty crucial.
Absolutely. Proactive consideration of the impact is always better than reactive.